Testing, testing. Just doing a mic check, mic check. 1, 2, 1, 2. Let's hop here. Your screen. YouTube, a beautiful mind here. Let's go like this. And this is going to serve as our lecture here. So we're basically continuing with our sessions on chapter 4 on integration. Right, and so this will serve as a lecture for section 4.5, integration techniques. This one is going to be substitution. A couple of objectives. We like to evaluate integrals using substitution, and we like to solve applied problems involving integration by substitution. Okay. All right, let's see. So we have the following formulas provide a basis for an integration technique called substitution. Okay. We have the integral of u to the power of r du, like that's like x to some power. Then, usually if we have x to some power, you got to add, say, +1 divided by r plus 1 plus some constant, assuming that r is not equal to -1. Right? -1, we would have natural log, like this one. Right? A recapping, either some x. This one is ln, natural log of absolute value of u. If u is what? Then it needs to be absolute value. If u is positive, then you can just do ln. But u is positive, right? So this is just kind of summarizing or recapping techniques that we've done in the past, right? Okay. Now, for y equals x cubed, we're asked to find dy. Y equals x cubed. I'm going to do like if we take the derivative on both sides, we can do the following. We can say dy equals 3x squared dx, right? I think of the name of that technique, like where we had it was in more than one variable. Look it up. I'm not going to look it up, but this is what, because like before when we were trying to find dy by dx, and so instead of moving the dx over, we're going to leave it like this. I think this is what they're looking for. So let's kind of leave it like this. I don't know why the name of that is slipping my mind. It's been a lot going on, but I'm going now. No, they did dy by dx, which is f prime, and they get this, and then through algebra you can move that dx to the other side, and they get the same thing that we got, right? Let's just keep going. This find du. So the derivative of this with respect to u, right? So again, if we have u equals x thirds, then take the derivative on both sides. So the derivative on the left is going to be du. On the right, the 2/3 comes down. We get x to the power of 2/3 minus 1 is going to be a -1/3. Then we need to put our dx. Get this and do 1 over the cube root of x, but I think that this will suffice for what we're doing. of u with respect to x, du by dx was the 2/3 x to the negative 1/3, and then like your algebra, you can move the dx to the other side, and you get something like this. This one to go, we have y equals e to the power of x squared. Right. So we can take the derivative on both sides. On the left, we're going to get dy. Now the derivative of e is itself. So we're going to have e to the power of x squared, but then we got to say times the derivative of the exponent. So the derivative of x squared is 2x, and then we dx. Yeah, that's right. I think that should be okay. So a power to another power, you can multiply, but I still feel like this is a typo. It should be the same thing because you can say, a power to another power. So e to the power of x squared should be the same as e to the power of 2x. But I'm going to leave it like how we got it, right? I'm going to leave it as e to the x squared, and we'll see if that pops up again. Because you argue for this form, right? That might actually be correct. Leave as an exercise for you all. Substitution, right? So we're at x. So now if we're gonna do this integral, like trying to do it directly, obviously you might not be able to do it, right? So then now let's try the technique of substitution. So we're gonna let you, let's try, now you just wanna try different u's, right? We're gonna start off with x cubed plus 1. So if that's our u, if we go ahead and take the derivative, then du is gonna be 3x squared dx, right? Notice you have your 3x squared dx. So that means that the u that we chose is more than likely good. So now what we want to do is make these substitutions into the original. So let's start with a copy of the original. We have the integral of 3x squared times x cubed plus 1 to the power of 10 dx, right? So now if we do our substitutions, this is going to be the same as the integral of u to the 3x squared dx. The u is going to be the x cubed plus 1. So now we're ready to integrate. So the integral of u to the power of 10, when you add 1, so it's going to be u to the power 11 over 11 plus some constant, right? Put our substitution back to the power of 11 over some constant. Over 11 plus c. 11 plus c. Right. Let me see. So they made their substitutions, right? You can see it here. They got the same result that we got. The integral of u to the power of 10. You do your integration, then you undo the substitution. So you work it back. As an exercise. Okay, so the challenge with these is just finding the proper u, right? So you might try to integrate it directly. If it doesn't work, then try this technique of substitution. And in the next section, we have one more technique we want to explore as well, right? So one candidate for u, we're going to say let u be, we got this 1 plus x squared. So if that's our u, then our du would be 2x dx, right? I keep wanting, so the thing earlier, I kept wanting to say partial fraction decomposition. Fixing up some terminology, but I just know how to do it. We can get to the bottom of it, but anyway, so here again, so we let our u be this guy right here. we went on and took that derivative. So then our du is 2x dx, and the 2x dx is there, right? So that's a good omen. So now let's do our substitutions, all right? So then let's start with a copy of the original. On bottom, we have this 1 plus x squared. On top, we have 2x. We got the dx over here, and we're taking the integral, right? So then if we do our substitution, have du over u. Integral is going to be what? The natural log of u plus some constant. Lay down. Boom. Like a couple hours. This is the lecture I owed you guys from Monday. I just never loaded it. So 1 plus x squared plus some constant. Natural log of 1 plus x squared plus some constant. Just want to go. To be 1 plus x squared. So then that means our du is going to be 2x dx, right? So you got your 2x dx. So let's make those substitutions and see what happens, right? This one's a little bit different than the previous. So now on bottom, you know, if we start, we have this 1 plus x squared under 2x dx, and we're taking the integral of this expression. If we make our substitutions, on bottom, we're going to have u squared. On top, it looks like we have du, and again, we're taking the integral. So this is really u to the -2 du, right? That's what we're really integrating. So the previous one is where the power is to the power of -1, so that's why we had to use natural log. But when it's to the power of -2, then I think we can just do it like normal. We can add 1 to the exponent. It's going to be 1 divided by -1, so like this. We essentially get 1 plus x squared on bottom. On top, we have like this -1 plus some constant. Essentially doing a quick derivative to make sure we started back with the original. So we got -1 over 1 plus x squared plus some constant. And you see it here, -1 over 1 plus x squared plus some constant. Okay. Bad so far. Kind of cruising through these. We're almost done, and I think I have enough time to go ahead and do the lecture for the day as well. Evaluate. Substitution technique again. We're going to let u be, we're going to let it be 3x. All right, let's just do that. All right, so dx, we get what, 3? So that's break it apart, because the log of the product is the sum of the logs. So we can break that apart into the natural log of 3 plus, I'm gonna see if that helps us. That'll give us two separate integrals to evaluate. Because this, as it is, what if we let u be x? Okay. If u were the natural log of x, then du would be dx over x, right? Okay. So this one didn't work, right? So let's try something else. So I'm gonna scrap this. This, right? So first, let's do this. Log of 3x dx over x, all right? Let me take it apart because the log of the product is the same as the sum of the logs, so we can break that log apart. And we can break it up into natural log of 3. I'm going to go ahead and kind of separate it all the way out. It's going to be natural log of 3 dx over x after distributing plus the natural log of x. To integrals that we're evaluating. Like this guy, I split it and then I distributed the dx and then I split the two apart, right? So these are the two that we're working with. Now this natural log of 3 is just a number, so we can just go in front. That changed, right? So that first expression is really dx. We're taking the integral, and this natural log of 3 is just a number that goes out in front. And if we let u be the natural log of x, so let me put plus, and then over to the side, I want to say let u be, so then our du is going to be what? Dx by x, right? So let's make that substitution. So then this is really u log of x into u, and then the dx by x was the du, right? I think that's just natural log, right? So x to the minus 1, when you integrate, is going to become just some number times the natural log of x. I'm going to come back to the constant. The integral of u is going to be what? U squared over 2. So we can say plus u squared 2 plus some constant back. So then ultimately it looks like we get the natural log of 3 times the natural log of x plus the x quantity squared. This is fine for now. All right, I think this is enough. Here, with this one. For live, you would have questions about this one, right? So that's why I'm trying to get this stuff loaded as soon as possible. Let me try to finish up not only this section, but the next one, and we can do an announcement about like materials, expectations, and things. Okay. Evaluate, okay, substitution. Oh, shoot. So they let u be the natural log of this, right? So then that derivative x. 3x. Because we can factor out a natural log of x, log of 3 plus natural log of x. A little bit more, we might be able to get to their conclusion. More we can do. So let's just add a page and see if we go right a little bit further, right? So now we got that natural log. Let's get a common denominator. All right, so I'm just gonna say equals. Two times the natural log of 3 times the natural log of x squared. I'm just rewriting 2 because I just wanted a common denominator plus some constant. Terms, we can factor out a natural ln x. Plus with the natural log of 9. The ln x over 2, right? If we factor that out, 2 natural log of 3 plus some constant. Power, that would be a 9. It's the same as the product. So then that would finish as x. Well, maybe it'll work out. So we have ln x over 2 times 9x plus some constant. I don't know. Let me look at what they did again. Because it's not like my right here. If this is your u, the derivative of this is not this, right? Here, right? The 2 comes down, and the derivative of ln of this is going to be du by u, so that's going to be 3 over the natural log of 3x. Okay. If you take the derivative, the 2 comes down, right? They're gone. This persists. Then you got to say times the derivative of the inside function. So the derivative of the inside function, I'm going to write it over here on the side. The 2 comes down, log of 3x times be what? Du, which is 3 over 3x. Cancel. Let's back up a second. So with this u, right? If u is the natural log of 3x, right? Then du is going to be x. Because it's x over x. So we just chose the wrong u. Is choosing the correct u, right? I still feel like what we did was not necessarily wrong, but if we can work it down to squared over 2 plus c, then we can stand by what we did. But I'm not getting scan over mine one more time to see if I can get it to work. And obviously this isn't the easier. We just chose the wrong u. We should have let u be the natural log of 3x because it does work. You just got to keep up with the algebra, right? But that 3 was kind of throwing me for a loop, so I split it. It became the natural log of 3 plus the natural log of x. Let me see, can we do that? And then this. So then that natural log of 3 goes in front. This integral becomes u squared. Out the ln x, you're going to get x. You're going to get of x. That's going to be the natural log of 9 plus the natural log of x, natural log of 9x. Where I'm making my mistake. I was going over it one more time to see if I could find my mistake. Please, that's so like distracting. Basically, we chose the wrong u, right? So let me just go ahead and do it with that proper u. And I think I'm just going to abandon this. And where I'm making my mistake. So I'm just where I just make those kind of mistakes, but that's okay. I mean, what we tried was okay. Just trying to, we're going to scrap it and just, I mean, I think we get it with that proper u, but again, like I say, the challenge there is essentially finding the correct u. So let's just do it really quickly with the proper u. So again, we're going to let u be 3x. du, so the derivative of natural log is du by u. So that's going to be 3 over 3x dx, which is, it simplifies down to dx over x. Dx over x, you got your u. So now we can substitute properly. You know what? I think the substitution wrong. But anyway, let's keep going. The substitution. I said our u was natural log of 3x. U du. You get u squared over 2 plus some constant, and then you substitute back. So then squared over 2 plus some constant. Okay. I like to leave those because you need to just be aware of like some of the challenges and pitfalls and how these things can go. Let's try another one. Okay. What if that was our U? Let U be x squared. Right? It's going to be 2x. Don't have a 2x dx, so we need to adjust this. It's x, so we can divide both sides by 2. So then we get half of du is going to be dx. So in order to produce the x dx, we got to incorporate half du. E to the, so this is going to be what? E to the u. That you can have a place to go. She's like licking herself and it just makes me want to throw up. And now I got hiccups. Like, I swear, it's like all this stuff is like converging. It's so funny. So du, but we got to multiply by a half. And I'm going to put my half out here just for the sake of simplicity. So I just moved the half to the front. Okay. So now that to integrate, the integral of E is itself persist. E to the derivative of E is itself times the derivative of the exponent. So squared is going to be 2x times a half, which gives us our x dx, right? I think this is good. I feel good about this. Right? Dx squared plus some constant. 1/2 e to the, oh, we forgot our c. So this, yeah, it's fine. I mean, they did it a little bit differently. So they know they needed the half, right? And I think I probably missed it. I'm glad I stopped for a second. So we started with x squared, x e to the x squared, right? But notice, now we needed this half. We can't just introduce the half without it being proper. So in order to introduce the half, that's going to be the same as 1/2 times 2, because it's 1, right? So then you can move the 2 around and you get this guy, the 2x dx, right? So then if our u was x squared, then our du was our 2x dx, right? So they multiply by 1 here so that they can get the proper dx, right? So multiplying by 1 doesn't change your result, it just changes the form. I think the way I did it might be a little bit off. I feel like this is the way you're supposed to do it, right? 2x dx. So now it has the proper shape. So then now we got our half, right? And then we get that result. Hopefully we can get another one of those. I want to try another one. We got, I'm not going to do that one right now. Let's give this one a go. Sorry, I didn't know you were there. Okay. Here, let's let you, x plus 3. Let's just start there and see what happens. Then our du substitution over u. So that is going to be the natural log of u plus some constant. The natural log of x plus 3 plus over x plus 3. Three plus a constant. So they let u be this, the du was this, they got the integral of the same thing. Okay, let's keep going. So again, the challenge is finding the proper u. We're going to say let's let u be, what is it? X squared plus 3. Let's try that. X squared plus 3. Then the derivative of that, our du, is going to be 2x dx. X. Right? Something with 5 halves. Yeah, like what they did before, they transform. Oh, shoot. That's in terms of x. Let's keep going. Let's just keep going. So we got a 2 and they have a 5, right? Something with 2 over 5. We could move the 5 out front and kind of ignore it, right? If we move the 5 to the front and we ignore it, now we have this 2x dx, but we want x dx. I'm going to kind of do what I did before because I kind of understood what I did. I don't know that that's correct, but it seemed like it worked, right? So when we're evaluating this, we're gonna, since it's all multiplication, we can move that 5 to the front and kind of ignore it, just let it persist. Dx, that means we need half a du. Should we multiply? Okay, I think we need to multiply by, do that 1/2 times 2 thing like they did. Okay, we're gonna try a similar way, because again, we want to have that 2x dx, right? Okay, we're gonna try something similar to what they did in the other example. Let's start by getting a copy of the original. We got the integral from 0 to 1, 5x times the square root of x squared plus 3 dx, okay? We can move the 5 to the left side of the integral so we don't have to worry about it. And we want 2x dx. So if we want a 2 in there, we need to multiply by 1 in the form of 1/2 times 2, right? So on the outside of our integral, we're going to have 5 halves, right? We're still going to have the integral from 0 to 1. Yeah, right? So we're going to have 2x times we multiply by 1 in the form of 1/2 times 2. I'm going to do those in blue. Change, we just multiply by 1 in the blue part that you see. So that way we can have our 2x dx, because that's what we needed. I think that's supposed to be x squared, right? I think I just accidentally changed it in the writing. Okay. To do our substitution. So this is going to be equal to, now I know the 0 and 1 should change. I'm not going to change it just yet. The 5 half persist, okay? All right. Square plus 3. So that's going to be the square, the integral from 0 to 1. And again, the 0 to 1 is proper, but I'm going to leave it for right now. The square root of u. Great. So u to the 1/2 becomes u to the 3 halves. So now we got the 5 half persists. It's going to be u to the 3 halves over 3 halves. So we don't forget it. But then we need to substitute back, right? So our u was x squared plus 3. Apply. So this is going to be what, 5/3 Now it's like as x goes from 0 to 1. And you get 4, square root of 4 is 2, 2 to the power of 3 is 8. X is 1, you get 40 over 3. When x is 0, three times the square root of 3. To 0, it looks like you finished with 5 times the square root of 3. For x, to the power of 3 halves. You can take the square root of 3 first and then cube it. I decided to cube it first. So then 27. So you're essentially doing the square root of 27. So the square root of 27 ends up being like was 3 times the square root of 3. But then that 3 on the front is canceled by this 3 here. So then you're left with 5 times the square root of 3. This is as far as I can take that one. So I'm gonna go with this result. But 40 over 3 minus 5 over 3. Let's see. Seven 3. I'm going to use my calculator. $40 divided by 3 minus 5 times the square root of 3. It's different, but result they gave an approximation. Let's compare and see what they did different, right? Because they did this a little bit different, but not by much, right? So first we find the indefinite integral, and then we evaluate the interval from 0 to 1, right? So they because remember I kept saying that the 0 to 1 doesn't apply when we do the substitution. So we could have just ignored it, which is essentially what we did until we were done with the substitution, and then evaluated over the interval from 0 to 1, right? So that's fine. So here's the original, right? Without the endpoints, without the restriction. So then, yeah, you had to make your adjustments. They multiply by 1 in this form. So that's what we did. We have our 2 over 2, right? From there, they kind of just rearranged it. They put this next to this. See it here. Then they did a u substitution. U was this guy, or du was this. Then they did the substitution of square root of u times du. Then something like this. That's blah blah blah. Let me see. that over the integral from 0 to 1. Where you crunch it down, and we got the same result, right? So yeah, with these, it can be a challenge following other people's work. Whenever I follow, like whenever I'm trying to follow somebody else's work, I do it myself first as best I can. The sense of what they're thinking. If I'm trying to follow theirs fresh, if I'm following theirs fresh and I'm like getting ideas, and I just watch to kind of get ideas. But it's not until you try it yourself and you sit with it that you actually can see the nuances. Um, but if you're trying to follow verbatim what I'm doing, it can kind of be it'll bore a hole in your head, right? So you just got to pick up what you can and then just keep trying and keep asking different sources. Ask me, ask your classmate, ask a tutor, research on the web, ask Pearson. You got to keep going until you find until something clicks, right? You just have to keep searching. Oh, so what we did was fine. And that brings us to the end of this section. Integration by substitution is a reverse of applying the chain rule of differentiation, right? So where we did chain rule, this is a way to undo the chain rule. The substitution is reversed after the integration has been performed, and then results should be checked using differentiation, okay? And in this section, those last couple of ones were a little bit dicey, but we made it. With that note, we're going to end the session here. Have one beautiful mind to another. Enjoy the rest of your day. Okay, guys, take care. Peace.